I'll just brief you on another colligative property, that is elevation of boiling point. Now you know what a colligative property is. Colligative properties are those properties of solutions that depend only on the number of solute particles present and not on the identity or nature of the solute particles. So the concentration of the solution or the amount of solute present in the solution decides the colligative properties. Now there are four colligative properties, that is a lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. Now in this video we shall discuss about elevation of boiling point. The other colligative property, that is lowering of vapor pressure, and the other two, depression of freezing point and osmotic pressure, are explained in other videos. Now what is a boiling point? We need to know. Now boiling point is that temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure. So when the vapor pressure of the liquid and the solvent becomes equal to that of the atmospheric pressure, then at that temperature the liquid starts boiling, or we call that temperature as the boiling point of the liquid. Now we know that when a non-volatile solute is dissolved in a volatile solvent, the boiling point of the solvent is elevated. That is, we need to heat more for the solvent to boil. It's very common, and even when in a day-to-day life we experience this. That is, when we boil pure water, it boils faster. But when you try to boil a sugar solution, or when you put sugar into it and then try to boil, then it takes longer time. Alright. Now this increase in boiling point, or the more time which we need to boil the water, is just this water of a solution is just because of the lowering of vapor pressure. We have seen earlier that when a solute is introduced into a solvent, the vapor pressure of the solvent lowers. Now because of this decrease in vapor pressure, we need to supply more energy to raise the vapor pressure of the liquid phase of the solution to equate it to the atmospheric pressure and to initiate boiling. Alright, so in order to increase the vapor pressure, we need to increase boiling, or we need to supply more energy for a solution. That's why the boiling point increases for a solution. Now that is depicted in this picture on your right side. So you can see here, when we plot a graph of vapor pressure versus temperature for a pure solvent and for a solution, you see that the boiling point, the boiling point of a solvent is at an earlier temperature, at a lower temperature than the boiling point of the solution. The solution curve remains always lower to that of the solvent curve. Alright, now this in this plot, the T0B represents the boiling point of pure solvent, T0TB represents the boiling point of the dilute solution in which the non-volatile solute is present, and the elevation in boiling point, that is the increase in boiling point, when you compare the boiling point of pure solvent and that of the solution, that is delta TB, the difference between TB and T0B. Alright, so there is an increase in boiling point for a solution when you dissolve, or you can say that the boiling point of the solvent increases when a non-volatile solute is dissolved in it. That is called elevation of boiling point. Now how do we relate, or how do we say it is a colligative property? Now we know that colligative property is that property which depends upon the number of solute particles. Let us see. Now the elevation of boiling point delta TB is proportional to the lowering of vapor pressure. We have seen that. That is, the boiling point increases for a solution just because the vapor pressure is lowered. Vapor pressure of the solution is lowered. So when boiling point is proportional to the lowering of vapor pressure, and we know that lowering of vapor pressure is proportional to the mole fraction of the solute. So logically speaking, delta TB, or the elevation in boiling point, will be proportional to the mole fraction of the solute. Thus, it is also a colligative property. So you can put delta TB proportional to chi b, that is a mole fraction of solute. Or you can put delta TB equal to K into chi b. Now chi b, we know that it is nothing but number of moles of B by number of moles of A, which is equal to, number of moles of B is equal to weight of B by molecular weight of B, and number of moles of A equal to weight by molecular weight of A. Now substituting that term for chi b, we get chi b equal to WB MA by WA MB, and we know that molality is equal to WB into 1000 by WA into MB. What we do, we multiply numerator and denominator over here by 1000. So our delta TB is rewritten as delta TB equal to K into molecular weight of A into molality divided by 1000. Okay, A is the solvent. So you can put it as delta TB equal to KB into M. The K and MA both are constant. K is a proportionality constant and MA is the molecular weight of solvent. Both are constants. So that can be put together and brought on. We can introduce a new constant, that is KB. KB is called the molar boiling point elevation constant, which is a property of the solvent. Now, the change in boiling point thus is proportional to the molality of the solution. The change in boiling point is proportional to the molality of the solution, or it is proportional to the concentration of the solution. Now, KB is a molar elevation constant, or it is also called as ebullioscopic constant. Ebullioscopic constant. Now, usually when we get delta TB, what we do is delta TB is added to the normal boiling point of the solvent to get the boiling point of the solution. It's obvious. You take the difference and add it to one of the add it to the pure solvent, you get the boiling point of the solution, the elevated boiling point. Now we have this expression, we shall try to relate it to the number of moles of solute. We have this expression, molality is equal to WB into 1000 by WAMB, and delta TB into K is equal to KB into, put the, substitute for M, WB 1000 by WAMB. And when you take the molecular weight of solute, MB is equal to KB into WB 1000 by delta TB WA, where KB is the ebullioscopic constant or molar elevation constant. Now, delta TB is equal to KB into M. When molality is equal to 1, delta TB equal to KB. So we can say that the ebullioscopic constant or the molar elevation constant is equal to the elevation in boiling point when 1 mole of non-volatile solute is dissolved in 1000 grams of solvent. 1 mole of non-volatile solute in 1000 grams of solvent is nothing but 1 molar. So the ebullioscopic constant becomes equal to the elevation in boiling point for 1 molar solution. Unit of KB is nothing but Kelvin kilogram mole inverse, or K by molality, Kelvin by molality. Okay, so the temperature is taken in Kelvin scale, not in degree centigrade. Now from thermodynamic considerations, KB, that is the ebullioscopic constant, is equal to RT0 square M1 by delta H vaporization. Alright, R is a universal gas constant, T0 is a boiling point of solvent, M1 is a molar mass of solvent, and delta H vaporization is the heat of vaporization of solvent. So that's the thermodynamic aspect, relation of KB to thermodynamic parameter delta H vaporization. So these are the points which I needed to introduce into you. Okay, now we can rewrite KB as RT0 square M1 by 1000 by delta H vaporization also. Alright, so try to solve problems related to the elevation of boiling point. and understand how we can determine the molecular weight of solute using by the knowledge of the elevation increase in the boiling point of the solution from that of the solvent by using the expression, the previous expression which we had for molecular weight, that is molecular weight is equal to Kb into WB into 1000 by delta TB into WA. Alright, so hope it's been clear to you. Thank you.